In this video, I'm going to go through the definition of an inflection point, how to classify them, and also go through an example. Before we start with the inflection point definition, we first need to define concavity. So a convex, we define a convex curve is when the slope is increasing. So if you look at the green curve here, and then a concave is when the slope is decreasing. So you have this shape. And you can see it like it's caving in. So knowing these definitions, we can now define the inflection point. So an inflection point is if you have a point C, so you're substituting C in the second derivative. We're looking at the second derivative now. And if at that particular point, your second derivative is equal to 0, and f changes concavity. So it goes from concave to convex, or from convex to concave. I'm going to show how this looks like in the next slide. At that specific point, so these two properties fit, then f has a point of inflection at that particular C. So this is when the curve changes from a convex to a concave, or vice versa. A bit confusing, but it's actually quite easy to see. So this is an example. So we have 3 different types of inflection points. If you can see, this is a concave down and then a concave up, or a concave and a convex. And then a concave. So these are different words you could use. Concave down, concave upwards, or concave and convex. So again, this is a concave down and upwards, and then this is a concave down, concave upwards, and concave downwards. So at this particular point, the second derivative is 0. This is what I defined in the first slide. So this is where the gradient on both sides of the inflection point has the same sign. So the concavity changes, but the gradient doesn't change. So if I do like a tangent on my curve, both of them will have a negative gradient. So as you can see, it's a negative here. What about this one? So if I have, this will be like positive and this will be positive. The sign stays the same between them. So that's different from stationary points, or turning points, sorry, where the signs change, because turning points, they turn the sign, the gradient. So these are not turning points. But they're inflection points because the gradient stays the same, but the concave changes. And then similarly here, you can kind of see it's almost a negative, but it's actually very close to 0. So at this particular point, the second derivative is 0. Let's look a bit closer. I'm going to take the first example. So summarizing what you've done before with the first derivative and second derivative. So this is the local maximum. We know that the derivative at the local maximum, the first derivative is equal to 0 at this particular point, whatever point it is. Maybe it's 3, so you substitute 3 in the first derivative, it's going to give you 0, and so on. And we know that the second derivative should be equal to 0, or using the critical value table. This is the local minimum. The first derivative is 0, and the second derivative is bigger than 0. This is your inflection point where the first derivative is not equal to 0, and the second derivative is equal to 0. Now, we need to be careful because there are some inflection points where both of these are actually equal to 0. So this is called a horizontal inflection point. So this is an example of one. So a horizontal inflection point is when the first derivative is equal to 0 and the second derivative is equal to 0. It means that the gradient at this point is parallel to the x-axis, because the gradient is 0. It means that the gradient is a horizontal line. It means that it's parallel to the x-axis. That's why we call it a horizontal inflection point. So basically what happens is, let's say you're testing stationary points and you find that A is a stationary point. And you want to test if it's a local minimum or a maximum. But if you're using the second derivative test, it gives you a 0. So you go, oh, it means that it's a horizontal inflection point. So let's look at this definition as well. So this is from this website. It's quite nicely written that all turning points are stationary points. So every time you have a maximum or a minimum, we call them stationary points. And turning points are specifically because they change the derivative from a negative to a positive. So if you have it goes negative, 0, positive, and then if it's a minimum, then it goes negative, 0, positive. sorry, positive, 0, negative. So turning points are stationary points, but not all stationary points are turning points. So there are some stationary points. So this is when the derivative is equal to 0, because by definition, if the first derivative is equal to 0, it means it's a turning or stationary point. So by definition, all turning points are stationary points, but if it's a stationary point, then it could be a turning point, but it could also be an inflection point. So a point where the derivative of the function is 0, but the derivative does not change the sign, just like I showed in the previous slide, where the sign stays the same between the inflection points. So if the derivative is 0, but the sign doesn't change, we call it a point of inflection or a saddle point. So it is a stationary point, but it's also an inflection point. If all of this is confusing, just remember this bit where if the first derivative is 0 and the second derivative is 0, then it's a horizontal inflection point. Let's go through an example. We have this curve, and we want to classify all the points of inflection. The keyword is inflection. So you first write the definition. You're like, inflection. I know for inflection, the second derivative is 0. So I'm going to find the first derivative, the second derivative. I'm going to use my bit of information and make my second derivative equal to 0. Now, this is a polynomial equation. It's a quadratic, so you either solve it algebraically or using your calculator. I'm going to solve it algebraically. This is a quadratic function. I'm going to factor it out. So I'm going to factor out 12x, and then I'm going to solve it. So either 12x equals to 0 or 3x plus 2 equals to 0, which means that either x equals to 0 or x equals to negative 2 over 3. Now, they want points, so you need to find the y-coordinates, and substitute, which means you substitute in the original function. So f of 0 is equal to negative 2, and f of negative 2 over 3 equals to negative 70 over 27, which means this is your final answer. These two are inflection points. However, you need to classify the inflection points. So what you're going to do is you're going to also substitute these into the first derivative and see what happens there. And you will notice that actually at this point, the first derivative is equal to 0. Which means this is also a stationary point, which means it's a horizontal inflection point. So in terms of classification, this is a horizontal point of inflection, or horizontal inflection point. And you can check all of this using your GDC. So this is you classifying it just to make sure that we answer all the questions. So we found them, but you classified them as well. So this is the actual graph. This is where your negative 2 over 3 will almost be at, and this is your 0. As you can notice here, so it kind of goes like this. So you can see that it is the concave changes. And then at precisely 0, you have this behavior. You're here. So it is a horizontal inflection point because you can see that it's a stationary point, but you can also say that it's an inflection point because the sign doesn't change on both sides. It stays the same. So hopefully this was clear. Make sure you use as many tools as possible. You answer the questions fully. But remember, inflection point is when the second derivative is equal to 0. And then you need to classify it a bit further by checking what happens at the first derivative as well, to make sure that either it's a horizontal inflection point or just a normal inflection point. Graphing it always helps, especially when you're practicing questions, just to understand what it looks like. For example, these three curves would usually help with understanding how inflection points would look like.